problem, which in the field is actually the hottest thing going in terms of interest. In terms of whether there's any skill or not is a very different issue. And so that actually is also very intimately tied to data assimilation, ocean data assimilation. And so I thought that I would include some background on that just because, again, it is very hot, and these data are going to be made available publicly for anyone who wants to look at them, so you can evaluate yourself if you think there's any skill, or try to find a novel way to see if there's any skill or not.
So which data will you make public?
Oh, so I'll actually go over that explicitly. Yep. Yeah, that's the big, one of the nice features. I mean, I can say one of the nice features about the IPCC, or the so-called CMIP project, is that they make all of that data publicly available to anyone who wants to download it. Of course, you do have to download it. So here we go, right? Okay, so I did want to make some corrections and clarifications from day one. I apologize, so I am a meteorologist by trade these days, so if I say something that's unclear, please let me know. I would appreciate if you could try to use a microphone. I have really bad hearing as I've gotten older. So the first thing I want to say is that I talked a little bit about this finite volume Lynn-Rood scheme, S.J. Lynn and Ricky Rood, and I talked about it being almost absolutely stable, and I said that was because it was implicit, and that's actually not true. Ravi pointed out when he is correct. It's basically a semi-Lagrangian scheme. Some people like Peter Lauritsen will argue that it's not, but it is certainly a scheme that's close in its flux form, but it's definitely not implicit. So then someone had asked about this, and I apologize because I realize some of you people are actually more pure math than a field like meteorology, and so an anomaly is actually just a deviation from some mean. The way that we use it in meteorology is some climatology. So for instance, the average over 20 or 30 years of January, if you take a particular case and subtract that, that would be, you could call it perturbation, we call it an anomaly. So other people asked about what we actually mean by seasonal forecast, and I apologize for not really defining that. And so the common nomenclature would be you make a forecast for some 3-month average of a field of interest, for instance, precipitation over India, for some period, let's suppose June, July, and August, and you start that from May 1st. So we talked a little bit about, or someone asked a question about the limit of predictive skill for seasonal forecast, and the answer that I had given for the Tropical Pacific SST, was about the order of 6 months. And so I was basing that on the skill level that's currently used, and so a common metric that's used is an anomaly correlation of around 0.6. So it turns out that when we look at things like SST forecast, we usually look at that in a deterministic way to evaluate the skill in the field. When you look at things like near surface air temperature, precipitation, usually you're looking at that in a probabilistic sense. So just to put that into a reference for you, so the Lorenz limit for weather predictability is 2 weeks, right? But you know that actually comes from this growth of errors, small differences in the initial state, and then just applying the model. So the actual weather forecast that we have anywhere in the world, no one is getting skill at 2 weeks, right? It's substantially less than that. So the realized skill is significantly less than what we would call in meteorology the potential predictability. So some people have actually done this same sort of Lorenz calculation with the Kane-Zibiak model, which is what would be called an intermediate coupled model, and look at, for instance, an index. So Lorenz actually did this with the ECMWF model for the Northern Hemisphere, 500 millibar geopotential heights, if I remember correctly. So Nemo 3 is the SST average in the Central and Eastern Pacific, and if you do this same sort of calculation, you get an upper bound of skill of 36 months. But again, realistically, you're looking at 6. Maybe some people would argue you're at 8 months of skill. But again, so 36 months would be the potential predictability in a Lorentzian type of error growth calculation for this particular model. No one's really done it with more sophisticated models. So then I wanted to point out that I made this comment about the atmospheric initial condition memory is gone in 2 weeks. And so someone asked me, I think after the class, then what use is the data assimilation to this forecasting problem? And the answer is that it's the ocean, and one day if we actually assimilate things like the ice and also the land, and that's where it would be, because that has a larger thermal inertia. If you're looking at something like the Madden-Julian oscillation, which has significant variability over those first 2 weeks, then the weather, or the atmospheric initial condition, could be important. Let's see. So there's another reason that the assimilation is important, and I'll show an example of this in terms of the real-time NCEP Global Ocean Data Assimilation System, which is run there in the U.S. That it corrects the model mean bias, especially the structure of the thermocline. Okay, so then, let's talk a little bit about this decadal forecasting problem. I'll actually have several slides about that. So the decadal forecasting problem has different SST anomalies that are important. The mechanisms are different. We would call this modes of variability in atmospheric oceanic science. And so initializing the ocean is important to capture at least some of these modes of variability. Again, this is an area of very active research, and I'll point out again that these IPCC CMIP current round will have these extensive set of decadal forecasts by international groups. I'll actually have an advertisement for that. Let's see. Someone asked, what do these skill maps look like for the current CGCM SST? So I'll actually show some of those from the NCEP coupled forecast system. The newest version of which has been installed in India as a collaborative project between the U.S. government and your Ministry of Earth Sciences. So then I just wanted to say, if you have any questions in the next few weeks or even after that, please feel free to send me an email. This is my email address. Make sure I spelled it correctly. And if you could just please put this in the subject line so I make sure that I answer it. Okay, so let's talk first about seasonal forecast skill of SST. So a point that I didn't talk about yesterday, but that is important, is the forecast skill on a seasonal time scale is dependent on the initial condition month. So what that means, for instance, is if you start a forecast in February and integrate out for 4 or 6 months, it's going to have lower skill, generally speaking, than one integrated from July or August. And the reason for that is that the Northern Hemisphere spring is a time when the system is weakly coupled. And so this is called the spring predictability barrier, and this is found for statistical and dynamical models, for complex dynamical models like we've talked about, GCMs, as well as intermediate coupled models. So every model that's currently used to exist Pacific SST has a spring predictability barrier. Some people will claim that theirs is better than others, but it's still a dramatic drop-off in skill. So what we'll do here is examine the forecast skill from this NCEP CFS. Sorry, this should be for, not or. 2 initial condition months, again, in January and in August. Again, for SST, for these purposes, you look at a deterministic score, the anomaly correlation coefficient. So then something else I'll show is I'll define a signal-to-noise ratio, just kind of a subjective measure of where you might expect predictive skill. And in this definition, the signal will be the ensemble mean standard deviation, and the noise will be defined as the deviation of the ensemble members about the ensemble mean. This is a common definition used in atmospheric and oceanic science. Okay, so here's the January initial conditions, and Weng-Chu Wang, actually I got these off of his web page, or actually this is the NCEP official forecast page. So the way that these work, again, it's seasonal means, which I would actually do the individual months, but that's fine. This will tend to higher the skill a little bit. And so NCEP has an odd habit of calling the first month 0 instead of 1. So anyway, this is the first lead, February, March, April, May, time going this way. And so you see here's the values of the anomaly correlation. So, at this 0 lead, you see that, you've already had some decay of skill. The Pacific here is obviously high skill, but there are some lobes of skill elsewhere. But as you go through time, you see that everything else kind of disappears except for the Pacific. This hangs out there, and again, because this is the thing that forces global variability, it's good that we get this right. Now, it's not good that it's as low as it is, but it's better than not having any skill at all. And again, using this subjective 0.6, you're getting some skill in this region, which is where it's important. Some other places you see, the North Atlantic is a place where you sometimes get a lobe of skill. This is actually not too bad. This would be, a several-month lead forecast over the Indian Ocean region, which could be important for simulating the monsoon. But you get the idea that as the skill decays, the Pacific is going to stand out, and the other places are just not going to be very high. Yes, sir?
Correlation with anomaly.
Yeah. So it's correlated with observed SST. So here's January, and again, same sort of idea, lead 0. Actually, that's not right. Sorry, it starts from August. So this is the first season, September, October, November, December, again, going down out through March, April, May. And so again, this is the time of year where you'd expect the forecast skill to start higher and stay higher. You see again these correlations in the Central and Eastern Pacific, and we'll talk a little bit actually at the end about these. And I apologize, I don't have the actual index map. But what I'll do when I'm done, when I get back, I'll send some more slides for the set. But anyway, what you see is that as time goes on, the skill in the Central and Eastern Pacific is higher in this case. You're retaining values of 0.7 or 0.8 at this longer lead. You're also getting skill in some of the other ocean basins at a fairly high level. Again, it's not a nice uniform region, but you take what you can get. This is the region of the Indian Ocean dipole, so being able to simulate SST variability in this region is pretty important. And again, North Atlantic is a region where we get a signal.
Can I ask?
Sure.
Regarding earlier this problem, for always at the equator,
Yeah.
correlation is always high. Right? The reason like that. Again, there is a local. Correlation is only concentrated higher value.
Right.
Only concentrated over the equator.
Yeah, so that's again exactly because of what we talked about yesterday. So that's these Kelvin waves that are propagating here and forcing these SST anomalies. And so this signal is being reinforced by the winds that are formed in response to the SST anomaly. So that's essentially ENSO.
Predictability.
Yeah, between 1/4 and 0.5. So you don't expect much predictable skill there. So indicating that the noise is just as big as the signal, if not bigger. I'll show another example of that in a different context later. Okay, so let's talk about this decadal forecasting and what that means. So there are two dominant modes of variability that people have kind of pinned their hopes on that you might be able to predict at the decadal time scale. Things that we know vary at a slow time scale, and I'll show you what they look like. One is called the Pacific Decadal Oscillation, or PDO. The other one is the Atlantic Meridional Overturning Circulation, or AMOC. So I'll talk a little bit about what we mean by decadal variability. Then there's the fact that there's interannual variability around the decadal variability. I'll show you what that means and what you could hope to get from it. It won't be being able to forecast 5 years from now what particular years. It's more associated with the statistics. We'll talk about what the challenges are to the decadal forecasts, and in particular, again, coming back to the relevance to assimilation, it's prescribing the ocean initial state. So if you're doing decadal forecasting, you're going to want to have as many samples as possible, and we'll talk about sample size problems with the seasonal problem as well. So that means you're going to have to go back in time into a period when there's very little ocean data. And so it's actually interesting seeing some of the Kalman filter talks. They reinforce recent talks in, recent results in reanalysis of the atmosphere by people also in that same group out in Israel in the United States, that the Kalman filter seems to be much more efficient at using sparse data than other methods, but perhaps that's a generalization that I'm making. And I'll talk a little bit about this decadal forecast data, which again, you can just download that on the internet and come to your own conclusions about the value of decadal forecasting. This is called IPCC AR5. Okay, so the first thing is this Atlantic Meridional Overturning Circulation, or AMOC mode. And so what happens is that there's this thermohaline-driven circulation, and there's a small wind component that's churning up deep water and bringing it northward. And so what happens is that this will have impacts if you affect the temperature in this region, and I'll pop up what's going to be affected. You're going to affect various things because this is a very sensitive region. The Atlantic ITCZ sits over here. And so here's how this region varies, North Atlantic temperature. So you see this is from 1880 to about 2000. These are SST anomalies. So you see that's got a fairly slow time scale except for a little bit of high frequency variability here in this period. And so if you were able to predict when you were going to shift from here to here, that would have impacts on various phenomena. Yeah, that's a good question. I think that it's been smooth. I think it's probably been smooth with about a 5 or 10 year filter. So, but you know, basically the sign is here, and then this has been smooth with a filter just to show the signal. But it's still it's still negative, right? And it's still mostly positive here, and there's negative and then back to positive. So it's a smoothing of the data to try to show the low frequency component. I'm not sure if it's a running mean. It could be filtered in a different way.
Is this from models?
No, this is observations. So I'm sorry. Yeah, this is observed Atlantic temperature, North Atlantic. No, it would be great if the models could do that, though. Yeah. Okay, so here is the warm North Atlantic, and you can again take this as opposite sign would have opposite effect. This is pretty symmetric. So it actually has drought impacts on the southern and mid-Atlantic U.S., leads to stronger hurricanes and more rain over the Sahel and western India. So a pretty strong set of teleconnections from this variability if you were able to predict it. So then the other variability mode is this so-called Pacific decadal variability. Principal mode, again, we use this mode perhaps differently than mathematicians would in the Pacific. This is what the pattern looks like. Sorry, get the arrows on there. Sorry. Yeah, so these are two different phases of the PDO. This could be called the positive phase, or this could be called the negative phase. And it's mostly a northern hemisphere phenomenon, and if you correlate what happens as this varies with precipitation globally, this is what the map looks like. So again, if you live in the southwest U.S. and parts of Mexico, if you were able to predict this on a decadal timescale or subdecadal timescale, that would be great because you would get pretty robust predictions of precipitation. There are parts of South America that also have robust predictions. Probably not too happy if it's a positive phase of the PDO in eastern Australia where there's been massive droughts and it would continue to be drought conditions.
El Nino?
This is different than El Nino, yeah.
You have a sort of warming just below the equator.
Yeah, so that's a good point, Chris. So this is actually somewhat similar to El Nino. It's wider meridionally. Okay, and so some people invoke one of the physical mechanisms for it. You remember we talked about the waves that reflect at the eastern boundary. The slower modes are wider in latitude, and so that contributes part of it. That doesn't contribute this part. And so what happens is that as this thing evolves, there's a wind stress anomaly. And the wind stress anomaly, the wind stress curl again in the mid-latitudes forms this lobe over here. Yeah. But it is similar to a wider El Nino in latitude, yeah. Not quite as symmetric.
The top two are also known observations? Or?
Yeah, this is all observations, yeah.
So they have that very smooth down. It seems like quite dense observations. They're up in some way or satellite observations? Or?
You mean the SST? So sorry, yeah, so the shading is SST, and the wind vectors are the analysis product. Yeah. So I'll sometimes use that as observations. Yeah, because we don't have anything else that you would have for a substantial period like that. So again, I mean, this is how this varies over time. It has a bit of a higher frequency than the meridional overturning circulation. But again, you seem to lock into fairly long periods where it's of one sign or another. And so it's people's hope, again, that if you could predict something like this, that you'd be able to predict longer-term trends over various parts of the world. Whether or not that will prove true is an open question. Okay, so here's the big problem with decadal prediction. So again, initialization. So there are actually quite a few global reanalysis products. When they make a reanalysis, what they're doing is they're taking all the historical data they have, and they go back and rerun the model and make a complete set. So for instance, they might go back to 1950 and run it up to 2010 at one time or as quickly as they can just to have a complete analysis. Many centers are producing these in Japan, Europe, the United States, and several in each of those places. But the problem is that there are many significant differences, especially on the things that are important to things like the AMO or fields that are important to things like the AMO. So salinity, we didn't talk about this yesterday. So density in the ocean is a function of temperature and salinity. And in many places, people used to ignore salinity, especially in the tropics, and that was very bad because it turned out that it had important effects, especially in the data assimilation problem. Because if you only assimilate temperature and you don't have a corresponding salinity change, you can introduce fairly large density anomalies, which near the equator can cause all sorts of vertical currents, which are unrealistic. So anyway, this is over time how this is the zonal mean, 12 meter seasonal anomaly, Atlantic average salinity. And so what you see is that even in the modern era, there are significant differences, right? So there's not much difference here, which is sort of interesting, but as you move into the modern era and you're actually getting some subsurface data, there's very great variability in the salinity. And then this is the North Pacific salinity, averaged over the upper 300 meters. And again, you see that there's quite a bit of variability, and then some solutions are quite different than others. And so what's reality? I mean, it's tough to say. You could take the ensemble mean and suppose that that's the best guess, but no one is going to initialize their model with the ensemble mean. Although it's tough to say, I shouldn't say that. Maybe some people will try something like that.
So there are no observations.
These are different data assimilation systems that are ingesting the available observations. So later on I'll show a map of what the observation network looks like historically. And there are two problems. So one problem is that it's very sparse to begin with, and the second problem is that a lot of the devices or instruments they were using to measure things, some of them only measure temperature. And so you only had temperature, you didn't have temperature and salinity. Now that's going to change. I'll get to that in a little bit because of what's called Argo. But we'll have to wait for an extended record there. Okay, so here again, same thing. This is the tropical upper temperature anomalies. This is integrated over the Pacific and Indian Ocean, so it's the zonal mean essentially. And so, and again, it's tough to say which one is correct and which is not. The most important point to make here is that they're different, right? And this is a 12 meter, and this is also the 12 meter. And for the Indian Ocean, I mean, around 1980 is when you had the tau array, and we'll talk a little bit about the tau array in a minute, come online. And so that strongly constrained the solutions, at least relatively speaking. And so you do see quite a bit of convergence of these solutions, although sometimes you do get an outlier. But in the Indian Ocean, they're just starting to get an array of subsurface ocean observations called RAMA. And so that these solutions are all over the place. Maybe they're getting a little bit better in the modern era, but still a lot of variability. The problem is that if you want to do decadal forecasting, in order to have a reasonable record, you're going to have to go back in time, into this 1950s and 60s period. And so you're going to have to initialize these models with this, subsurface temperature field for observations. And so that's why I was saying before, it seems that maybe the Kalman filter would be something that can make better use of the observations than some of the other assimilation techniques. I should point out that at least two groups are likely to use the Kalman filter. One will be GFDL, which has an ensemble Kalman filter forecast system, and the other will be NCAR, which has Jeff Anderson's ensemble Kalman filter data assimilation system. Okay, so again, this is just a schematic of showing how the observations have varied as a function of time and depth. This is for the global oceans, as I recall, and so this is the depth from 0 down to about 2 kilometers, and so this actually starts over in the, can I get rid of that? Is that possible? Sorry, I think so, right? I just hit it with the thing. Okay, great, sorry. Yeah. So if you go over to starting around 1980 and then up to about 2006, you can see how the observing network has changed and what the density looks like. And so, not a lot of observations, certainly almost none down below 1,000 meters. And so it's commonly believed that to do the AMOC problem, you really need to have this data, because this is some of the water that will get churned up over that time scale. And as time goes on, you start to fill in, and then this huge spike of data that you see, especially going much deeper, this is associated with Argo, which is nice, but the problem is that now you only have about 5 years of data. So another issue in ocean data assimilation is, so suppose that you're doing a retrospective analysis, and then you make forecasts from it. So you have this amount of data in this period, and then all of a sudden you have this greater amount of data. What does that do to the mean state? Are you going to introduce what will appear to be huge anomalies just because you have a much better observational record? This is the global ocean. Yeah. I'll show horizontal maps.
Sorry, before you go, the color scale?
Yeah, so these are in thousands, and I don't remember if this is thousands per month, or probably that's probably on the order of what it is. Yeah. Yeah, so it is per month, yeah. No, not a lot. I mean, you see this gray stuff. Yeah. We have enough trouble getting observations up here, so yeah.
I guess Argo gives up.
No. Yeah. Yeah, so the original Argo design actually was only for 1,000, and then they actually found that they could adjust the instrument and make it dive deeper. But yeah, I think 2 kilometers is about the limit. Yeah. Yeah, so then let's talk about this time scales of variability again. This is for observations. This is for a point in central Colorado. And I'm not going to tell you how I do this decomposition technique, because as mathematicians you'll beat me up about it, but I can talk to you offline. Let's just suppose, for the sake of argument, that my variance adds up to 100%. And so that's what these red lines are, these red numbers are. So this is for the annual mean temperature anomaly. This is for the annual mean precipitation anomaly. You can definitely tell that it's the US because we're using Fahrenheit and inches. And so this is what the record looks like in terms of anomaly over this period. This bouncing up and down line, black line for the annual mean temperature, so I'm not looking at anything subannual. So I can correlate that figure with the global mean temperature, and I'll call that climate change, so it's varying in phase with the global mean temperature. Okay, then I can remove that from this time series, and then I can use some filtering again, which I'm not going to describe, which I'll call the decadal part, which has this variability. And then you can remove that from what was left, and then what's left is actually the interannual part. And the important point is that the interannual part has the largest part of the variance, right? So if you're going to try to describe what's going to happen over some period, knowing the interannual characteristics would be important. It doesn't mean that you necessarily have to predict the peaks and troughs, but knowing the variance or extrema would be important to know. It's also important to know what the natural decadal part is. And so these modes that we just talked about, for instance, this AMOC and the Pacific Decadal Oscillation, are things that would fit into this natural decadal variability. So you see the same sort of behavior here for the precipitation anomalies. An important point is that the so-called climate change signal, the part that varies with the global mean temperature, is very small for precipitation. And this result holds outside, this is not just a central U.S. Phenomena. I mean, this holds throughout most of the globe. Again, the natural variability and the interannual variability are about the same order of magnitude, but the interannual part has most of the variance, and so it would be very good to be able to quantify this. And so what you might want to do in these sorts of experiments that they're going to conduct is look at how the frequency or the statistics of this interannual variability varies. Do you get more warm events over a particular period versus cold events? I actually have a slide that talks about this a little bit. Yeah. Yes.
So annual mean precipitation.
Yeah. Yeah.
So that would be the, when you talk about climate change signal.
Yeah, so that's just the part, so I'm going to do a linear regression with the global mean temperature, and that's what this line is. So that's just the part that's varying with...
Global mean precipitation.
No, global mean temperature, right? Because the forced signal is the global mean temperature.
Okay.
So sorry if I didn't explain that. Yeah, so no, we're regressing against the global mean temperature, what varies with the global mean temperature.
And this would be the deviation from the mean at this place in Colorado.
That's correct.
And it's the average, the rainfall over the entire year.
That's correct. Yeah. So again, from the longer time scales, just like with the seasonal trick where we looked at seasonal mean instead of looking at individual months to try to get some signal out of the noise by averaging, hopefully. It's the same sort of idea, but year to year, because you're not expecting to get actual seasonal variability, but you could look at the statistics of the seasonal variability. Does that make sense?
Yeah. But in some ways it's not surprising because, there's a total amount of water in the world which is conserved, right?
Sure.
In the whole climate system.
Sure.
Is that enough to explain why you see a signal in temperature and not in precipitation?
Well, that's a good question. So you know that as the Earth is warming, that the moisture is actually going up.
Right.
The warmer atmosphere will hold more moisture. So I don't know if I've answered your question. Probably not.
But only at one place.
But it's only at one place.
This is a place.
Right.
Yeah.
The global average.
So you would see in some places the signal might go down. And some
Oh,
places
sure.
it might go
Oh,
up.
sure. No, that's true. So if that's what you're asking, no, not everywhere there's the precipitation going to be monotonically increasing.
Those that things can now cycle faster.
The moisture cycle could be faster. I mean, that's one thing that people have hypothesized, and some of the model results certainly point to that sort of conclusion being valid.
But would you see that in this?
No. You would need to look at distributions, latitude, longitude.
Rapid change was by regressing against the global
Global mean surface temperature.
indication.
Oh, so I'll talk to you about that later.
That's the only which you said.
Okay, so again, so what's the value of that interannual part, right? And so I kind of got into that a little bit. So suppose we have these decadal forecasts, right? We are going to have interannual variability. In fact, they're going to have diurnal variability. So what you could do with this interannual variability is you could look to see, you know, for a several-year period, try to characterize the statistics of that variability and see what it is. And you can ask questions like, what's the probability that we get into these little acronyms here. So this is January, February, March rain that exceeds some threshold at some location or some region. What's the probability of increases in extreme events for heat or cold or rain? And so that's the sort of information you could use. And so that's the sort of information actually that infrastructure planning people want. So an infrastructure planning people, that would be a U.S. Euphemism for politicians. And so, you know, there is a large part of this issue being driven by political considerations. People want to know, do I need to build a dam that will withstand this range of rain, or roads that have this temperature range that they can survive? And so, you know, to be fair, and again, so I should also point out, to be totally fair, I'm not doing decadal forecasting. That's not because I don't think it's an interesting problem or that it will fail. It's just that, you know, we're not into that game where I'm at. So there is a question, although I should also say a lot of my friends are doing it, friends and colleagues. So there's an open question. Will we be able to do it? Will the forecast have any skill? And so the answer is nobody knows, right? But the only way you can evaluate that sort of thing is actually to do the forecast, and that's what this next round of the IPCC is about. Let's see. What's that? Yeah, so again, and again, this will be in your slide set in case you have any interest about what actually is being done. And so as part of this IPCC AR5, these coordinated decadal predictions, so there'll be these 10-year integrations, hence the decadal, with initial dates every 5 years from 1960 to 2005. Ensemble size is recommended to be 3. I mean, to be honest, that's ridiculously small, but they're trying to encourage people to get in. We'll talk a little bit later about multi-model ensemble, so maybe you could get some information out of that. They're hoping that people will do order of 10 members. My guess is that that's what most groups will do. They've asked that ocean initial conditions should be some way representative of the observed anomalies or the full fields for the start dates. That means you'll have to use some sort of an assimilation system to get the subsurface ocean data. So originally when people tried to do decadal forecasting, they tried to do what would be called a forced coupled initialization, where you just take the observed sea surface temperature and you force that at the lower boundary of the ocean and the atmosphere. And that will actually spin up a circulation and has some useful properties, but it won't let information penetrate down to those deeper levels. And they leave it free to what you want to do with these other things. They're asking some people if they want to have what they call extended integrations, which would be 30 years long. And again, the ensemble size is awfully weak. But anyway, so this data, and if you send me email, if you have trouble, you know, if you Google it, will be available online. As with most of these experiments, you know, they set a date when they think they'll have it done, and Then, like a year later is when it actually gets finished for various considerations. At least that's not fair. They'll all get the data into the serving center, but there will be issues with serving the data. So that data should be served, though, I would guess, within the next 6 to 12 months. Okay, so let's talk about the current and historical state of the ocean observing system. So a lot of discussion during the week about the observations and the importance of the observations in the data assimilation problem. The problem in the ocean is that we don't have very good observations. That even includes SST if you want to look at multi-decadal records. So the first satellite-based products, and I talk about that because that has global coverage and uniform statistics usually. They started in around 1982. Actually, they started specifically in November 1981. So you only have about 30 years of data. So think about that. When you're talking about seasonal forecasting problem, for instance, you have 30 data points that you can look at. It's not like weather forecasting where you run a weather forecast every day or 4 times a day. Therefore, you have 300 or 1,200 samples. You have about 30 years if you rely on that SST. So there have been some clever people who have derived these EOF or SVD reconstruction techniques so that you can go back when you only had ship data, which is very sparse. We'll see what that actually looks like a little bit later. But these products actually don't compare all that well in the common era. So a test that I like to use with respect to these is that the satellite-based SST product and the ship-based SST product will both produce data for the modern record, and you can compare how they look. Assume that you're kind of comparing one as observations and the other as a guess, and unfortunately they don't compare all that well. And so an issue with this is that when you have these reconstruction techniques, you build the EOFs on the period when you have the good data, and so then you're taking those patterns and projecting them back in time. So there are issues about whether you can use these data sets. In my opinion, there are issues about whether you can use these data sets for determining things like trends and patterns of variability. On the other hand, let me say that it's very nice to have these data sets. Some of these data sets now go back to 1900, and so you can do a lot of useful things for them, but for some things they're probably not as good as you might like. Let me say that. So on the subsurface, the big thing was this Tau Triton array, which started around 1990 to present, and it's there sometimes. And I'll explain what I mean by sometimes and show you an example because that's important. So these actually are very expensive to put in, and they have to be maintained by ships. And so it's very nice to have those to be the observations that anchor the ocean assimilation in the Pacific, but they'll blink on and off. So Rama, I'm not even sure if it actually has officially started yet. That will be a similar array in the Indian Ocean. Prada is in the Atlantic, and Prada has this same problem with sometimes.
Are those moorings that are supposed to be?
Yes, these are all moorings, yep. And so Argo is basically everywhere. I'll show you a map that starts in earnest around 2000 and fills in till now. So as we've discussed before, this is great. The problem is that you're only going to have about a 10-year record, and that's when it started, and it's been filling in slowly. Okay, so why sometimes? So certainly there's wear and tear on these things out in the ocean, but then there's this little story I'll tell you about. Okay, so the buoys that dandelize sit in this cold tongue, which is very good for phytoplankton and zooplankton to live. So the small fish come and eat the phytoplankton, and the big fish eat the small fish, and the fishermen come to catch the big fish. They do all sorts of interesting things to the buoys, and so I'll show you a record of the buoys blinking on and off. And what's happened is that it's not necessarily intentional, but they'll tie their boats to the buoys, they'll climb on the buoys, and they break. And when they first actually put the Tau array in, they tried to have a program where you could get a coupon, every few weeks where you would get reimbursed. You agreed not to go within a certain distance of the buoy. But they've discontinued that, and they have a lot of problems in these ones in the cold tongue, which is sad because it's the cold tongue that actually is where the thermocline is coming to the surface, and that's where the coupling is most sensitive. Okay, so here again, let me talk first about this consistency of the observed data sets. So these are actually 2 data sets generated by the same person. This is Dick Reynolds. So the optimal interpolation V2 is the modern era data set, uses the satellite data. The ERSST, this actually might be ERSST2, is a EOF reconstructed SST. So this product uses satellite data and ship data. This product only uses ship data or any other XBTs that might be around. This is the period that it's over. So if you correlate these two, This is what it looks like. This is the scale here. So there are some places where the correlation is pretty good, 0.7, 0.8. But, right along the equator, for instance, it can be pretty low. It can be down to 0.3 or 0.2. And again, the important thing is that these are two estimates of the observations. And so the question I would ask is that if the RSST, and in the modern era you have more shift tracks than you do back before 1982, if it doesn't agree very well with the product that we would consider ground truth, for instance, the OI, how reliable is it when you go back into the 60s and 50s when you had very little data? Okay, so if I look at the root mean squared difference between these two, that's what this looks like. And if I look at the relative standard deviations for these two, here's the ER, here's the OI. So the first thing to notice when you compare the standard deviations, a lot less variability. Not surprising, less observations for the EOF reconstructed. There's some similarity between them, quite a bit. Basic structures, which again, is not too surprising because this product is built on the EOFs of this. But then if you look at, again, the root mean square error in some of these regions, and the color scale is the same, root mean square error can be on the same order of magnitude, on the order of 50% of what the interannual variability looks like. And so again, I would say that this kind of tends to indicate that these EOF reconstructed SSTs have some problems. So what that means in a practical sense is that if you look at centers that are doing data assimilation operationally and they go back in time to generate what would be called retrospective reanalysis, and the forecasts would be called reforecasts, they'll start in 1982, or they'll start in November 1981 because that's when you can get the satellite SST.
So, both the data sets, the standard deviation is large in some regions, exactly where the correlation is large.
Yeah, so fair enough. So go ahead.
Basically, it's broadly equal, which is low all across.
Yeah, so the point that Ahmed is making is that where the variability is largest is where they agree the most. Fair enough. Yeah. Okay, so here's what these arrays look like. This was in 1999. This is in 2008. So this is all of them along the equator. Of course, in 1999, you had nothing in the Indian Ocean. Here's the Tau. Here's the beginnings of Parada. And then 10 years later, you move in, they establish the Triton part of the array. And this is kind of plans for where they're going with the Rama. And here's Parada. They've added some. They have, various things they have besides SST and salinity, including sometimes now they have carbon dioxide, various biochemistry, certain surface fluxes. So this essentially is what's getting assimilated into all these operational centers, this subsurface data. That's the constraining observations in addition to the SST and the surface wind stress forcing that's used to produce these operational data assimilation products such as GODAS, ECMWF, Jim Carton's SODA product. Each dot is one buoy.
Where are the ones working?
Oh, I'll show you. Yeah. So So this is where the cold tongue is, and so what you'll see is that what will happen is that these buoys will come out, and in the Atlantic. What's really sad is that this is in a really important region in the Atlantic, both for oceanic variability and for precipitation variability up in the Sahel and down here over the Gulf of Guinea, and these will go out all the time. What's the lifetime of those buoys? So some of these buoys went into 1990 and they're still the original equipment. What will happen is that NOAA will send out what they call a maintenance cruise, and the maintenance cruise is supposed to go up and down and service all the buoys. But what frequently ends up happening, again, because these buoys are very important, is that the maintenance crews will be out doing some work, and some of these buoys will go down, and they'll have to come back and fix them when they can, because it's not that fast a process, right? So to do the whole array, I think, is on the order of a year, and it's not cheap either. And in modern times, it's tough. Okay, so why did they arrange that buoy array that way? I mean, it was very very carefully thought out. And so first reason is that there was not a lot of money, it was expensive, and so you wanted a minimal set that can do the job, right? And so if you remember, we talked about this delayed oscillator theory, and you saw that the waves had certain structures in the meridional direction. And so they knew, because the planning for this array was going on about the same time that these theories were being developed for what was causing the variability. And so they took that into account. People at the Pacific Marine, I forget what the E stands for, let's suppose that it's Environmental Laboratory in Washington, who actually also involved with running the buoy program. And so they're the ones who set up that structure. The other thing is that the ocean currents are meridianally confined, so in the north-south direction, they have a very compressed structure, but it's very important. Advection can be important in the equatorial ocean, so I'll just show you quickly what I mean by that. Yeah, so this is the result current. This is the date line. The date line, for those of you who don't know, is 180 degrees. And this is depth. Sorry, it's upside down. I apologize. So this is the surface. This is the deep ocean. And so the first thing you see is that the strong currents are confined to the upper ocean. This is called the equatorial undercurrent, north equatorial countercurrent. Again, you see that these currents are mostly confined within about 15 degrees of the equator. If you look at the tau array, you'll see that it's maximizes. I think it ends at about 17. So that's the maximum latitude limit. So the meridional current, also at the date line, looks like this. And again, the meridional current has a smaller scale for the most part, strongly tied to the equator. And so again, that's why the resolution is in this region. The upwelling itself is even more meridionally confined, and so some people actually, when they put the tau in, were concerned this structure could be important, so I apologize, I haven't gone over the colors. So these values are positive, so upwelling is actually occurring over a very narrow meridional region. That's what's bringing this cold water to the surface. But you see there's downwelling that occurs, and this is again because of this Ekman pumping mechanism on either side, and so you need fairly high resolution to recover the downwelling. Other people will argue that if you get the innervated effect over this, which you can do over a few degrees, that it's okay. Ocean models typically have a resolution in the equatorial region between about 10 north and south of a third of a degree, so that they can resolve this circulation. Meters. This is down to about 400 meters. Okay, so this is, GODAS is the Global Ocean Data Assimilation System. This is the assimilation system that is produced at NCEP, the Operational Center. Actually, it's NCEP EMC, Environmental Modeling Center, sorry. Dave Barringer is the one who leads that program. And here's the tau. So that's the tau we just looked at. So this will be along the equator, or averaged about a few degrees of the equator. This is January 2010. About every 1 week, they're looking at the observed temperature anomalies. And then this is the difference from GODAS, the GODAS minus the tau. And so what you see is that there's a warm anomaly here, and then there's a super warm anomaly, because this is the difference GODAS minus tau that occurs, and actually in time it grows, right? And so by the time you're out into this period, this thermocline anomaly that you get that's in the upper ocean, GODAS is extremely deep with that, and in fact it's going to intensify it to be much stronger than it is. And so the problem with that is that this did not develop into an extremely strong El Nino. When you're prescribing this basic state, it can be very sensitive and go off and produce false El Ninos, and that's exactly what happened with this model. And so here's the... Oh, am I causing trouble? Resonating there? Sorry. Yeah, so sorry. Yeah, thanks for saying something. Okay, so here's the tau Triton array, and this is like a traffic light. So green means that you're doing pretty okay. The availability of the sensor is 80 to 100%. Yellow is kind of getting concerned, 60 to 79%. And if it's available less than 60% of the time, and you can actually get these statistics from the tau website, and it's this red color. And so what you see again is over here in the east, these buoys went out due to vandalism, and it took a long time to fix them. Also the one on the equator, unfortunately, which is the most important one, that's where the upwelling is occurring. That's also where the fish are. It also went out to vandalism. And then, there's another example of the same sort of thing later on. And here the comparison will be, this is for the July case, and again, you see what the warm anomalies look like. You see this tremendously strong error that's occurring, and this is another assimilation product. So what this says is that, the GODAS is also having large errors with respect to this assimilation product, and so that, this is partly a model problem or partly a model and assimilation problem. So there are other models that are not having as severe a problem with the missing buoy data, so that this scheme in the GODAS in combination with the ocean model is more sensitive to the loss of that data, probably because of the systematic biases in the background model. At least that's my conjecture, and that was theirs as well. Okay, so the future is brighter, though, for ocean observations. The Argo array is going to be there. So again, I said 1,000 meters. I do think that it has been adjusted to be 2,000 meters. So these things are kind of neat if you've ever seen one. They're about this high, about this wide. They're bright yellow. They put them in the water. They activate them with a magnet, and they'll dive to about 1,000 or 2,000 meters and then come back slowly, and they do this several times. Then they stay on the surface for a while, and they transmit the data to a satellite. So by now we have nearly global coverage for the world's oceans. They measure both temperature and salinity. And one nice thing about it is that it's multinational, so many countries bought buoys. And so when I say a country bought a buoy, so for instance, Germany bought a buoy. It doesn't mean that they have a buoy just outside Germany. Usually they're buying it in some region of the ocean which was considered, as they filled it in, to be most important. So for instance, the tropics. So here's a distribution of Argo floats. And I apologize, you can't read this, but this color map actually shows who bought the buoy, right? And so you see what the global coverage looks like. It's awfully good. One thing that's curious that still plagues people and annoys people in the U.S. is that the Gulf of Mexico is almost empty. And this is in 2007, and the map of 3 or 4 months ago still shows that it's empty. I don't know why the U.S. just doesn't buy those buoys. Because again, this is a very important region for things like hurricane formation. So again, this is just a map of the moorings, and then these are just examples of ship tracks. So before you had the TAL array, and which is 1990, and certainly way before you had the Argo floats, this is what the ocean observation looked like. These single tracks that move through, and so, and again, this would not be. I should point out, this is not contemporaneous in time. This is over a full month. It could actually, I'm not sure that that's actually accurate. It could be over longer than a month. And so not a lot of observations in the ocean. Yeah, not much going on down here so far. To be honest, given the way things work, I mean, if you're monitoring things like climate change, then you could perhaps argue that these are very important. But for driving the world circulation, you really want the stuff between plus and minus 15, and then some of these other isolated warm water regions.
But the big difference between moorings and Argo floats is that Argo floats float with the
current.
with
That's
the
right.
current.
Yes.
So
these will move in time. Yeah.
Right? That's sort of an issue.
Yeah, that's true. And so actually, I believe that it's correct that they actually can be moved back. I'm not sure of the method for doing it, but yeah, because people, of course, realize that with currents that they would move. Okay, so here again, historically, pre-Argo, this is what temperature looked like. Temperature measurements in the Indian Ocean, salinity measurements, and this is a scale. I think the scale, again, is observations per month. And this is Argo. This is what the Argo observations look like. So again, filling things in quite nicely. Salinity record, just about the same as the temperature record. Should actually be identical, I guess. Okay, so the point I wanted to make here is that, as you've seen, as we've seen, there's a lot of places, again, in the historical record where there's not a lot of data. And so what that means is that the models are going to determine a large part of the solution. So in these data-sparse regions, and for certain fields that are not observed, for instance, most people these days assimilate temperature. As Argo comes on, they'll assimilate temperature and salinity. A common thing that was done recently was to take the temperature assimilation and then make a false salinity correction to keep the column gravitationally stable. Sometimes that's called synthetic salinity. But the currents are never assimilated. And so what ends up happening is that the currents can vary substantially among these products, even for those using very similar observed data sets, very similar observed models, especially near the equator, again, because the sensitivity of currents to pressure perturbations near the equator. But the problem is that makes using these ocean estimates as a verification product problematic or more ambiguous. So these are labeled in a politically correct way. This is ODA 1, ODA 2, ODA 3. To be honest, I don't even remember what they are. But these are the currents in January, surface currents. This would be the average, let's suppose, over the upper 15 meters. And so color bars here. So these greens through reds are positive, and the kind of aqua to purple are negatives. And so this particular model, so this is actually positive. What this means is that this model has the equatorial undercurrent surfacing at this time of year. This model has easterlies all the way along, kind of this weird lobe structure, although both of these produce that. This model has a very different structure than either of the others. More recent satellite observations would suggest that this is actually much closer to observations, or available observations, than either of these two. But these are all from major centers. These are actually major reanalysis products that lots of people use. Okay, so let me return a little bit to this coupled model bias or systematic error problem. And so a few points I wanted to emphasize. The first is that the SST errors are frequently on the same order of magnitude as the seasonal variability. Sorry, shouldn't be capital. Or which are measured by the standard deviation.
Can you just
Go back. Oh, sorry, wrong way. You wanted this one.
So these are are the differences in temperature so much?
In the Pacific, where you have the TAL array, so you have a good observational database, the differences in temperature are less but not zero. In a place like the Atlantic, where you have very sparse for most of it, this period is around the order of 1982 to 2004. So over in the Atlantic and the Indian, where there was not a lot of data to constrain it, the subsurface variability will be very different and will largely depend on what wind stress data set forced the model.
I'm basically thinking, will people use these data sets for forcing the atmospheric model? They choose one or the other based on their preference?
So usually what will happen, what the big centers will do is that they have complete systems, right? So if my center is producing this assimilation product, that's the assimilation product I use. Small centers have the luxury of choosing which one they think might be more realistic. Okay, so again, to return to this coupled model bias issue, SST errors can be on the same order of magnitude as the seasonal variability. So again, the signal is the same size as the noise, and this will really be apparent in the Indian and Atlantic Oceans. So the other thing is that these SST errors are ubiquitous across models, or similar across models. It doesn't matter what model you have, they all display very similar sorts of errors, which for a long time people thought would be great, because then if someone else fixed their error, then you could find out what they did and it would help you to fix theirs, but unfortunately no one's ever been able to fix them. The equatorial SST variability has a wrong spatial structure and amplitude, and again that's important, and I'll just show the Pacific because that is the El Nino variability. And then the precipitation structure becomes distorted and too symmetric about the equator, so this will have bad effects not only on how ENSO evolves, but also the global response, because it's that convective anomaly that's forcing the upper troposphere angular momentum field. And this is called the double ITCZ syndrome, and again, this is in all models. Some people have less of it. Some people have a much worse phenomenon, which was where the ITCZ, which should only sit in the northern hemisphere, will actually flop back and forth across the equator.
Can you remind us what ITCZ is?
Sorry. Intertropical convergence zone. Yeah. Okay, so here I'll show CFS, and I should apologize. I'll send Ahmed an updated copy. These are actually from Wang-Chu Wang's very nice website at CPC. So this is a forecast starts in April. This is what they would call the 1 month lead, June, July, August. Again, as time goes on. So the first thing to notice is that even at 1 month lead, this general error structure is the same, right? So you're getting this warming here on the southeastern oceans. You're getting this cooling along the equator, and it will grow in time as a function of the annual cycle. And depending upon when you start the forecast, it will be more or less severe. But this is a very common set of errors. Warm errors here, cold errors here, And by the time this thing gets spun up after 5 or 6 months, these errors here can be on the order of 3 degrees. This error here can be a couple of degrees. And so that's fairly substantial. It's enough to move precipitation distributions around in bad ways, or unrealistic ways. So I apologize, the color scheme here isn't all that great. But again, this is this SST standard deviation. This is from the observations. And so what you see again is, not surprisingly, the standard deviation of SST, largest in this central and eastern Pacific along the equator, associated with El Nino. But in these regions where we have those errors, you see the standard deviation is maybe on the order of a degree, or between 0.5 and 1 degree. And so where we have those very large errors, the SST variability is actually of a smaller magnitude than that particular error. Okay, so this is a different model. Actually, this is a model of mine, and this is just to emphasize, and don't worry about the mid-latitude stuff. This is just to emphasize, again, that this sort of error is ubiquitous across the models. We see the cold tongue, my cold tongue error is worse than theirs. That's because of an excessive precipitation response to SST in my model. But the warm error is also here. And again, also in the Atlantic. I apologize, I should have split the continent. But you can see that the errors are basically the same. And if you pick up anyone's coupled model, that's what they're going to look like within 4 or 6 months of forcing the model. Let me point this out. So these errors in the mid-latitudes are actually due. This ocean is about 1 degree by 1/3 of a degree, so it's 1/3 of a degree meridional near the equator to get that equatorial wave structure, very fine, get them upwelling. These errors actually are known to be due to using, and it's 1 degrees only, these errors are known to be using coarse resolution, and for some problems like the Gulf Stream, that would be considered coarse resolution. If you have higher resolution, horizontal resolution, these errors would go away. I mean, this just means it can't resolve the Gulf Stream, and so it's not correctly transporting the water associated with the Gulf Stream. Okay, so let's look at this standard deviation of SST along the equator, what it looks like. So this is starting from January going through June. This is observed, so you kind of have a maximum of variability. So this is, again, what I was talking about is the spring predictability barrier. Things get weak, and SST anomalies get weak, the wind stress gets weak, upwelling gets weak, and the variance of the SST gets weak. And then it starts to come back as the seasonal cycle onsets again. That's observed. This is what the model looks like. And so again, so the model actually starts out with a real strong signal. It then dies off. You don't actually see this sort of weakening that you're supposed to. And so I would say that this is not a particularly good simulation, but you'll see this is a fairly common type of error pattern. And again, this sort of thing will be a function of the seasonal cycle. So these are starting in August and going through January. This is the observed. So you're maximizing variance towards the end of the year. And then in the model, you do that fairly well, but the magnitude at which you start is quite a bit too big. They're talking in here about a degree or 1.2 degrees. You're up in here 30% too strong. Some models will get this extremely strong at this time of year. The error here could approach 50 or 80%. Okay, so this is the so-called double ITCZ. So here's what the observed looks like. So Chris had pointed out, so this is called the ITCZ in the Pacific. This would be the Atlantic ITCZ. The ITCZ over land, over here, over Africa. And this is actually called the South Pacific Convergence Zone, and it's supposed to have an orientation kind of like this. From the southeast to the northwest. What happens in the model associated with this warm error and this cold tongue is that you get precipitation along the equator goes away, and you split this feature, and the SPCZ becomes very zonally oriented. So that's why it's called a double ITCZ. Instead of having this asymmetric structure, it becomes very much like this feature is mirrored in the southern hemisphere, and this has really bad effects for things like simulating El Nino. Some models have made progress in fixing this, but it's still present in some level. Yeah, this is probably She-Arkin, which they have an acronym for these days. I forget if it's GPCP. Okay, so let me talk a little bit about the use of multi-model ensembles in seasonal forecasting. So how do we use that, right? So we have a set of forecast systems, each which has its own ensemble members. Suppose there are 10, 20, something on that order. And so what's been found in various experiments and various centers that have team together is that if you take the forecasts from one system, and combine them with other systems, you get more skillful forecasts. So you could say, well, is that just due to the fact that you're increasing the ensemble size? Suppose that you had 50 ensemble members because you had 5 groups with 10 members each, and instead you had the best model, best in quotes, and you had 50 members of the best model. And so people have looked at that in a few cases and shown that even in that case, that for reasons that are not exactly known, but suspected to be error cancellation, and just the different physical formulations, that the multi-model ensemble will be best. What's also somewhat surprising is that most of them are equal weight. Part of that is that, again, seasonal forecasting, you have about 30 years of data. So if you're going to make a cross-validated statistical scheme, it's very difficult to get unequal weights doing that. It's also been found that even if you do that, that frequently the equal weights are as good as the unequal weights. Now, I should point out that these are metrics that are evaluated globally. If you look at some particular region, so for instance, suppose India, it's possible that you could find a set of weights that are unequal that are better. But if you took the aggregate average over all of the tropical land points, generally speaking, the equal weights are as good. Okay, so what does that look like? So RPSS is ranked probability skill score. That's a probabilistic measure of skill. So here's a set of 1-tier forecasts. Here's a set of 2-tier forecasts. Let's start on the 2-tier. So these are for June, July, August, 1-month leads. That means these started 1st of May. So all 6 members give this profile for ranked probability skill score. And what this shows is the y-axis is how many grid points exceed this value of the ranked probability skill score. And this is what it is, RPSS, the actual skill. And so RPSS below 0 is no skill. And so again, all 6 members has this skill. If I just look at the AGCM, that's this blue line, and then these 3 other lines are actually the component models of this AGCM3. So the first thing to see is that the blue line is generally speaking above each of its components that make it up. And then so when I say all 6, I'm taking the AGCM and I'm adding in the CGCM ones. And so that going to 6 members gives you higher skill yet. And so here, and this is for temperature, and so this again is the same sort of thing. This is for the coupled models. Sorry. Yeah, and so if I look at the CGCM, that's this blue line. All 6 again is the red line, same thing. And so you're seeing that the CGCM actually is almost as good as all 6, but you do get some improvement from including, which would be the difference between these two, by including the 1-tier models in this lower range of the skill. So how are we doing on time? 1 minute? 5 more minutes. Okay, so I'll skip this. You'll have the slides. It's the same sort of result. These results are very similar. So there have been several big projects, especially in Europe. One was called Demeter. The major participants in that are European Center, UK Met Office, Media France, and then they had a follow-on experiment called Ensembles. And these are all very similar, consistent results that they find. So this is just an example of what you get if you take a whole bunch of, and these are the models that I'll talk about. These are actual forecasts that have been conducted over this period. And these are the various models that are used. I apologize, I know the color scheme and the symbols are hard to see. And the black line is actually the observations. And so what you see is that these different forecast models, they tend to envelope the observations, right? And so if you actually were to break this down, which I'm not going to do, we don't have time, you would tend to find that sometimes some models are better than others. But by including all the models in this, it's kind of the equivalent of a spaghetti plot, I guess. You're actually doing a better job of capturing the mean signal. So I'll skip this and this, and again, that'll be in there. So I'll just talk for the last 5 minutes about what's called Observed System Simulation Experiments, or OSSI. Right, so again, these observing systems are very expensive. They're very important, but they're very expensive. And so, especially in the United States, there's been a tendency to say, can we turn off part of the tau array? What if we did that with that damage forecast skill? And so what you can do is run a set of experiments which measures the value of the observed system. So you run the ODA with the full data stream and then run a set of forecasts from it. And then you remove various parts of the observing network, run the full ODA again, and then again run the forecast system. And then the difference between these two is a metric of the value of the forecast, of the different data streams. So here's an example of that, and various groups have done this. This is an example from the Japanese, and these are different SST regions. So Nino 1, 2 is in the west, 3 is this one that's Central Eastern Pacific, this is Central Pacific, Western Pacific, Nino West, I'm not even sure what that is. Subtropical Indian Ocean and the Western Tropical Indian Ocean, sort of the Indian Ocean dipole, and so this is root mean square error, so it's better if the bar is lower. So the value of the root mean square error for using all the observational data is white. If we take out the tau Triton array, then it's blue or purple, and if we take out the Argo, then it's orange. And so what you see is that generally speaking, the white bar is lowest, but it's not always true, right? And so if, for instance, you take out if you take out, in the Nino 3 region, if you take out, take out the tau Triton array, the root mean square error goes up from about 0.5 to closer to 0.6. In Nino 3.4, it's even more substantial than that, about 0.45 up to about 0.58 or so. Why sometimes when you remove part of an array or a full array, it's got better skill than including all the data is interesting, but people are not spending a lot of time trying to evaluate that. So anyway, I think that's the topics I wanted to cover today. Thanks for your indulgence. I guess we're about on time because we started late. But thanks. It was very nice to meet all of you. Again, if you have questions, please send me some mail.
There have been attempts to predict the regime change in the two things using standard time series model. Because there are very good time series techniques to be able to capture the regime change using under the Markov framework.
Which regimes?
The El Nino, La Nina.
Oh, yeah, I think there have been certainly Markov model studies of El Nino, La Nina, yeah.
And how good you could, how well you could use those results, predictions, into your more differential-based model.
Yeah, so that's an interesting question. So what has happened is people have actually made just Markov models of the process, but to actually do what you're saying and include that, no one that I've known has done that yet.